Hey everyone, and welcome to our next lecture video on exception handling. So what exception handling allows us to do is to have error checking code within our programs. And this code can check and detect any sort of errors that may occur, and it gives us the ability to recover from those errors within the program, thus making our programs a little bit more robust. So let's start off looking at the syntax for the exception handling. And in Python, we use a try block followed by an except block. So the try block is where we're going to put any code that could cause an error. So just like with other blocks, we're going to have to indent, and we'll put all of the code in here that could cause an error, such as opening a file or dividing by 0 or something like that. And then if an error occurs within the try block, then execution is going to immediately jump down to the except block. And this is the code that we want to have execute when the error occurs. So in here, we could do something like ask the user for a different file name if we couldn't open the file because it didn't exist, or just print out a nice message rather than a stack trace like we normally get. So let's look at an example here. In this example, it's just a random number guessing game. So I'm importing the random module up at the top. We are going to generate a random number between 1 and 10, and then we're going to ask the user for a guess. So notice that that guess must be able to be converted into an integer before it is stored in the guess variable. So right off the bat, we should be thinking, well, what if a user puts in something different, like the letter A or the letter B, then we can't convert that to an integer, therefore we're going to have an error here. Okay, the rest of the program just goes on to see if the guess was the same as the random number, then print correct, else then it was wrong. So what we're going to see here is essentially what we just talked about. When I run this example and I enter uh, a letter instead of a number, that letter cannot be converted to an integer. So guess A, and we get this trace back, and it's telling us ultimately that a value error occurred, and it's saying that it's an invalid literal for the int function with base 10, and it even tells me what the input was A. Alright, so if we're going to start using exception handling, then some of these errors are going to mean a little bit more to us. Like, we know that this is a value error. Well, let's see how we can recover from this value error and maybe not have this sort of message print out to our user. So I modified the previous program we just looked at, and I took the code that could be problematic and I put it inside this try block. So inside the try block we have our guess, and that's where we are converting the input to an integer. So if someone does enter A for the input and they try to convert that to an int, it's going to generate a value error, and immediately code is going to jump from line 7 all the way down to line 13. It's going to enter this except block and start doing whatever's in this block. So in this particular case, I chose to just print out a message letting the user know that there was invalid input. We could build on this. We could put this in a loop and have the user keep entering things until we get valid input. Uh, that level of detail as far as exception handling is completely up to the author of the program. Okay, so now rather than getting a traceback like this, when I run example and I enter A, it's just telling me that it was invalid input. Alright, so we can build on that. We can have multiple exception handlers. And the idea behind this is that problematic code could generate many different types of exceptions. So in this traceback, we saw a value error occurred. That's one type of exception that could happen. Another one might be dividing by 0, and that's going to be a totally different type of error. So we could account for both of those here if we wanted to. So let's just talk about what the syntax here is doing. We have the same try block, and the try block again is indented, and that's our code that could cause an error. And then we have our first except, followed by the exception type. So this exception type would be whatever we're seeing from our traceback here, the value error, or whatever other type of error. We've seen name errors, value errors, um, whatever comes out of this traceback, we could pull that out and then place it right after the except. And what happens is if that exception occurs in the try block, then the code is going to jump to this particular except block. So if that exception doesn't occur, then maybe there's another one that we want to account for. And if that one happened within the try block, then the code would just automatically jump down to this except block. And then kind of like how we have an else when it comes to ifs, that we can also just have an except that doesn't specify the type of exception that is trying to catch. So if we just have an except here at the very end, then anything that didn't match any of these ones above it is going to immediately just jump down into this except. Okay, so here's an example of that. In my try block, I'm grabbing two numbers, num1 and num2, converting them from input to integers. So we already know that this right here can generate a value error. And in fact, we can see down on line 9 where we're accounting for that. We're saying except this value error, invalid input. On line 7, I try to compute the quotient, being num1 divided by num2. Now, one thing that can happen when we are dividing is if num2 is 0, then we will generate a zero division error. Okay, so again, jumping back to here, it would say zero division error right here, and we would know that we could catch that in our exception block if we ran it without the except down here. Okay, so after we compute the quotient, we're just going to print out that num1 divided by num2 equals this quotient. All right, so real simple program here, just trying to illustrate that only one of these except blocks is going to execute, and it's going to be based upon the type of error that's generated. And if no error occurs, then neither of these except blocks will execute. All right, so here's three different executions of that program. So the first one, enter 1 for num1, and then an A for num2. So when I did that, value error was generated right here on line 5, and the code jumped down to 9 and entered this except block for the value error, and it printed out invalid input. In this one, I entered 1 for num1 and 0 for num2. Well, we know that that's going to generate a zero division error, and it jumped down to that except block right here and printed out that you can't divide by 0. Lastly, if we enter everything correctly, 1 and 2 for nums 1 and 2, then we get 1 divided by 2 equals 0.5. So neither of the except blocks executed there because no exception or error was generated within the try block. All right, so taking this a little bit further, we can actually create our own exceptions. So, for instance, and this is a little bit trivial because there is a zero division error that will be generated if we try to divide, but let's take a look at this example where I'm entering two numbers again, A and B, and before even doing the division, I'm checking to see is B 0, because if it is, then I'm going to raise my own value error here, and we can provide optionally a message when we raise an error inside the parentheses as an argument. So I'm saying raise this value error and say that you can't divide by 0. So I'm doing this before the division takes place, so it's not going to generate a zero division error. Instead, we're creating our own custom value error. Okay, so when we try to run this and I enter my two numbers, and as you can expect, I'm going to try to run this with a 0 for num2, then it ends up stopping on this line for raise a value error, and we see at the very end we have a value error, and then there is that message that we provided. All right, so that's the significance of the message. And the main use case for when we would want to raise our own exceptions would be typically inside of functions that we created. So here we're going to look at exceptions with functions, and functions had the option of either handling exceptions or raising them for someone else to handle. And any exceptions that are raised in a function can be handled by the caller of the function. Okay, so if we call a function from main and that function decides to raise a value error or any other type of error, then we can actually catch that back in main and do something with it. So let's look at an example of that. Here I have two functions, getNumerator, which is just going to return this input converted to an int, and then getDivisor, which is going to grab this input, convert it to an int, and check and make sure that it's check to make sure that if it is 0, we want to raise this value error. If not, then let's return it back to the caller. So what we have here are two different functions that could raise errors. The first one, which is implicit, right? It's not explicitly written here, would be a value error that came from this if we tried to convert something like a letter to an integer. That same value error could occur here on line 5 if we tried to convert, say, a or b to an integer. But then again, there is also this explicit value error that gets raised in the event that d equals 0. We're going to say that you can't divide by 0. All right, so down here in our program, we're calling, or we're setting up a try block, and we're calling that getNumerator and getDivisor. Either one of those could generate multiple value errors. Right? There's 3 in total that could happen here. And if one of those happens, then the code's going to jump down to this accept, and we're seeing that it's accepting the value error here. Now this is some new syntax for us. We can take this value error and assign it to a variable by using this as something syntax. So EX is just a variable name that I created. We could call this anything we wanted to. But when we try to print that, if we try to print EX, we'll see that it prints out that nice message that gets passed in. Okay? So again, this part is optional. We don't have to include the as EX, but it's one way that we can capture this particular exception that's being generated or error that's being generated and store it into a variable and use it within our accept block. So let's look at an example here. If I run example and I enter a for my numerator, then it just prints out invalid literal for int with base 10 a. Okay, so where did that message come from? Well, if we jump way back to one of our first examples here, you'll see that the value error that got generated when we entered something like a actually contained that message. That was a pre-done up message that the Python library created for us. So we can leverage that and display it to the user without showing them all of this stack traceback stuff. All right, the next part, I just sort of iterated through all of the examples here. If I enter a 0 for the divisor, then we get that you can't divide by 0. We would get the same thing as this message if we tried to enter a letter for the divisor, because it would also be caught by the except. And then lastly, we have our successful example where we enter 1 and 2, and we see that 1 divided by 2 is 0.5. All right, so one of the last things we want to pick up out of this particular module is this notion of a finally statement. So we can clean up our try excepts with a finally. And this is an optional clause of the try statement, so it doesn't have to be there. And it's executed regardless of if an exception occurs or not. So it doesn't matter if one occurs, the finally will always be executed at the end. So what would we want to put in there? Well, this is usually a good spot for us to clean up any sort of resources that were being used, such as open files. So here's our syntax. We have our try block. We know that that's where our error could occur. We have an except block, and this is what we do if the error occurs. And then keep in mind we can have multiple except blocks, and we could follow them up with the type of exception that would be generated. I didn't include that here in the syntax. And then ultimately we can have a finally at the very end, and this is where any cleanup actions are always executed. So let's look at an example and try to make sense of that. And let's just walk through this. It's a little bit overwhelming at first. Data file equals input file. So we're grabbing a file path from the user and we're going to store it in this string. And what we're going to do is in this file there's going to be numbers on each line, and we're going to just total up those numbers and print back to the user what the sum is. Okay, so total is going to hold that summation for us as we go through and we're iterating through that file. So in our try block, we are going to have an open our file, so f equals open data file. We know that this may cause an I/O error. This may cause an I/O error if that data file does not exist. Okay, and just to show you, because I don't think I included an example of that actually happening, but let's say f equals open temp blah.txt. So that is a file that does not exist, and we get this file not found error. Well, file not found error is a subset of an I/O error. So if we try to accept an I/O error, then it's actually going to catch this file not found error as well. So I know that that's probably a little bit confusing, but there's hierarchies of different errors that can occur, and ones that are lower in the hierarchy can be caught by ones that are higher in the hierarchy. We also know that as we're iterating through our lines in that file, that the line, when converted to an int, could generate a value error, as we've seen several times previous in this lecture. So once we have iterated through each line, we'll just close F. And actually, line 9 is not needed here. I'm not sure why I left that in there, because that is the whole point of finally, is to have finally go through and call that f.close for us. Okay, so we have two exceptions that can occur. We have our file not found exception, or IO error here, and we're just going to print out a nice message. We have our value error, and we'll print out a nice message. And then we have our finally block. Okay, so in the finally block, I had to do a little bit of extra work. I had to check to see if f was in the visible variables, or was f still in scope here. And the reason why is because if an IO error occurred here on the open, then nothing would have ever been assigned to f, and the f variable would have never been created. But if we got past that, then f would be created and it would be an open file. So what I'm doing here is I'm checking to see, is f in my variables? If it is, then just print out that we're closing this data file and then close it. Lastly, I'm just printing up the summation that we computed up here in the try. Alright, so let's take a look at what execution looks like. I've got three different well, two different data files. We're going to try three different data files. I have data.txt that contains 1, 2, 3, 4, and 5. All right, so that's sort of our success case. That should work. I have data2.txt that contains 1, 2, 3, A, and then 5. All right, so that's testing to make sure that our value error actually gets caught here. And then I have this data3.txt, and that file does not exist at all. Okay. So if I try to run this, then on the first one, when I enter data.txt, we don't expect any problems, and we see that message that is closing data.txt, and then it prints out the summation, which is correct. We should be seeing 15 here. On the next one, I try it with data2.txt, and I actually hit an error saying that we could not read number from data2.txt. That was when it came across this A. Okay, it still goes into the finally block and prints out that it's closing that data file, and then it closes it. Ultimately, it then follows that up by printing out the sum. So notice that the sum is 6 here, and you may be wondering, why is that sum 6 when it should be 15? And that's because it is summing up all the numbers up until it got to the A and that exception occurred and it quit. So 3 and 2 is 5, plus 1 is 6, and that's where that number came from. So on this last one, we're trying data3.txt. We know that it doesn't exist. We see that our I/O error got caught, and it's printing out that it couldn't open that file. Notice that we don't see a closing data3.txt, and that's because F is not in my vars, right? Because the exception happened here before the assignment was done. So since it happened here, it jumped, printed, jumped, checked to see if it was in the vars. It wasn't, but we do still see it print out the sum. And that's why it says sum equals 0. Alright, so that wraps it up for our lecture on exceptions and error handling. If you have any questions, please feel free to reach out to me. If not, I hope you enjoyed the labs and exercises this week. Thank you.